Okay, this lecture is for what is energy. We are starting a very long unit on different types of energy. So the first thing we need to do is talk about what energy is. It says energy and persistence conquer all things, and that's from Benjamin Franklin. That is particularly relevant to this class. The goals are that you should be able to define and label the major types of energy. You should also be able to convert between the major energy units, joules, calories, and so forth. And you should also be familiar with LOCE. LOCE stands for the Law of Conservation of Energy, and that's something that you're going to be working with quite a bit and is the fundamental principle behind the whole energy unit. So energy is defined as the ability to do work, which isn't particularly useful unless you know what work is. Now we're going to talk about work more in the context of the next chapter, but just for now, energy is the ability to do something, to apply a force, to move something a certain distance. And so the wind has the ability to manipulate this turbine. It can push the turbine blades a certain distance. Okay, whenever you have a nuclear reactor, the heat has energy and it can move a turbine. This neutron right here, when it hits this uranium atom, it has a certain amount of energy that is capable of splitting or applying a force and breaking these atoms up. Energy is the ability to do work. So if it can apply a force over a certain distance, then the object is said to have energy. There are many different types of energy, but a couple of the ones that we're going to talk about are chemical, nuclear, solar, mechanical, potential, thermal, and electrical. Now we'll get into more specific details about what each one is as we move through this presentation. But suffice it to say, the vast majority of things that we'll talk about in this class will come from one of these major types. Energy units. So all energy is measured in the standard unit of the joule. It's named after this guy right here. His name is James Joule. He did a lot of work with the laws of thermodynamics, which we'll talk about a little bit later. So the standard unit, or the SI unit, is the joule. You may be more familiar with the calorie in the United States because that's the unit of energy that you tend to see most often. Calories you tend to see on food, but really it should be in joules. Now, 1 calorie, okay, 1 calorie is the amount of energy that's required to move 1 gram of water 1 degree Celsius. But really, that is the equivalent of 4.184 joules. Now, one thing that's very, very important is when you look at a nutritional label, if you were to go to some other foreign country, so European countries, a lot of times this is in kilojoules, but even if it's in calories, they put this little K right here. It stands for kilocalories. Remember, kilo means 1,000. That doesn't mean that if you were to eat this particular thing, that it would be 350,000 calories and you'd gain so much weight. Really, in the United States, 1 capital C calorie is equal to 1,000 lowercase c calories. So we don't distinguish between a kilocalorie and a calorie in the United States, but it's very important that you be able to do so in this class. 4.184 joules, which joules is the standard unit, is equal to 1 small c calorie, okay? Or 4,184 joules would be equal to 1 big C calorie. And finally, the other big conversion that you have is kilowatt hours. If you ever look at your electricity bill, you would see that the energy is measured in kilowatt hours, not in joules or calories, because the numbers would be enormous. You're talking about something like an average house can use between 2,000 and 4,000 kilowatt hours per month. If you look at 2,000 times this number, your bill would be, in terms of usage, would be very, very large and very, very difficult to calculate. So instead, they use a larger unit of the kilowatt hour. So the law of conservation of energy is going to be the fundamental principle behind everything we talk about. And it's this. You should have learned it in chemistry. It says energy cannot be created or destroyed, only converted from one form to another. So you have this massive annihilation. You're colliding these particles together very, very quickly. But the energy is not created. The energy is not destroyed. It's only changed from one form to another. Okay, this example says we have 200 joules worth of gasoline, which is actually a very small amount of gasoline, that is burned and converted to electricity. It says how much heat is produced if the reaction is 80% efficient. Now, what that means is we have the law of conservation of energy. The law of conservation of energy says that if I have 200 joules to start,
I have to have 200 joules to finish. Now, that doesn't mean that all the energy is producing electricity. In fact, it means that some of it is used to produce heat. And in fact, you can use this efficiency, this percentage, to determine how much is each. So, if the reaction is 80% efficient, what I can do is I can say 200 times 0.8, and what that does is that gives me 160 joules. What that would be is that would be the amount of electricity that's produced, because it's 80% efficient, which means 80% of the energy goes where I want it to go. Well, remember, no matter what, I have to have 200 joules to finish. So what that means is that there's a missing 40 joules. And that 40 joules is the heat that's generated as a result. Law of conservation of energy is going to hold because I have to have 200 joules on each side. Now, only 160 joules is usable, stuff that I can use in terms of whatever I want to do to light a light bulb or so forth, or something like that. But I have 40 joules that is lost as some sort of excess energy.
So chemical potential energy is our first type of energy, and it's the energy that's contained in the chemical bonds of a substance. So if you have something like oxygen, oxygen is a diatomic molecule, so it has two oxygen atoms together that are bonded to make an oxygen molecule. Well, the fact that there's this bond, they share this energy, is chemical potential energy. Because that energy of that bond can be released if it's combusted or some sort of other reaction occurs, and it can make atoms move away, it can make atoms heat up, and so forth. One of the best examples of chemical potential energy is in fossil fuels. So right here you see oil. The oil has a tremendous amount of energy in it, and it's the main reason why we use it for producing gasoline and fuel in our cars and so forth, is because it has such an enormous amount of energy per weight. You also have things like batteries. Both of these are examples of chemical potential energy because a chemical reaction can occur and release that energy. Nuclear energy. Nuclear energy is the splitting of a uranium-235 atom or the combining of two hydrogen atoms to produce large amounts of energy. So the splitting of a uranium atom is called fission, and it creates lots of heat and is used in nuclear reactors. The earliest nuclear bombs, atomic bombs, were actually fission bombs. Okay, the newer nuclear weapons tend to be fusion bombs, and the reason why is they produce a lot more energy. The only place that fusion really occurs at is in a thermonuclear bomb and on the sun. Okay, everything else in terms of a reactor would be a fission reaction because we aren't quite able to control a fusion reaction sufficiently in order to use it to produce energy. The next one is solar. Solar is pretty obvious. It's the energy that comes from the sun. All energy that we have on Earth is derived somehow from the sun. Okay, we have hydrocarbons like oil, but oil used to be plants that were alive that later decayed, and those plants got their energy from the sun. Okay, you get your energy from, let's say, a hamburger, and that cow got it from the grass, and that grass got it from the sun. So all of the energy that we have on Earth originates from the sun. Gravitational potential. Okay, this is the potential energy that an object has due to its position in a gravitational field. And that may sound somewhat confusing, but if you have like a rock and you hold it above the surface of the Earth, if you were to let go of that rock, well, there would be work done on that rock because that rock would fall. It would move a certain distance with some sort of force, and because of that, there's some sort of energy associated with it. So we call that gravitational potential. We also have elastic potential. So if you are trying to shoot a slingshot at somebody, you can actually take it, you can stretch it really far back, and you can give it a tremendous amount of energy that will shoot the rock much further. So there's elastic potential energy, which is the energy that's derived from the temporary deformation of an object. So if you were to take this thing and stretch it back, you are temporarily deforming it. Okay, when a basketball is bounced on the ground, it's temporarily deformed as it pushes together and then moves back upwards. Thermal energy is the energy that occurs due to a difference in temperature. Okay, thermal energy is not the same thing as temperature. It is the difference or it is the energy that is transferred as a result of two things being different temperatures. Electrical energy, this is the energy involved with the movement of charge, and this is going to be the source of many more lectures later on in the second semester. The key thing though is energy is always transferred between forms. So we've already talked about the law of conservation of energy. And that says however much energy you have at the beginning is equal to the energy that you have at the end. So what happens is energy is actually transferred between forms. So for example, if you were to lay out in the sun, okay, you would actually heat up and you would get really hot. And the reason why is that solar energy is converted into thermal energy. Okay, this is the same thing that occurs right here when you have a solar water heater. And what happens is the sun collects on this solar panel and it pumps it into a heating tank where you have water, and that solar energy is converted into thermal energy.
Okay, this question says, starting with the sun, map out the flow of energy that ends with you running down the hallway. So remember, we always start off with the sun, and we have solar energy. Now, solar energy goes to Earth and hits the leaves of plants, where it is converted to chemical potential energy. Okay, at that point, the chemical potential energy of the plants could be eaten by a cow, could be eaten by some sort of bird, which later then you eat, but at this point it still remains chemical potential energy. So even if you eat something like a piece of fruit, it's chemical energy. If a cow eats grass and then you eat the cow, it's still chemical energy. Okay? Once you have this chemical energy that occurs, you then eat this and you have this chemical energy. That chemical energy is then converted into mechanical energy, which is involved in the movement of objects. And finally, the energy of motion, a subpart of mechanical energy, is kinetic energy. And we'll talk more about kinetic energy in a couple of presentations down the road, but for now, suffice it to say that kinetic energy is a smaller part of mechanical energy.
So now you should be able to identify and define and label the major types of energy. You should be able to convert between calories, kilowatts, big C calories, little c calories, joules, kilowatt hours, all of those you should be able to convert between. And you should also be familiar with the law of conservation of energy.